All right, let's talk about the Hilbert basis theorem. So what it says is that if A is a Noetherian ring, then A adjoin X, i.e. polynomials in A with one variable, polynomials in one variable is also a Noetherian ring. And this is kind of long, but apparently it's important, especially if you like algebra. You'll probably have to do arguments like this again, so let's do it. So what we're going to do is we're going to prove that every ideal of A adjoin X is finitely generated, because if every ideal is finitely generated, then that's equivalent to it being Noetherian. So let's take an ideal B in AX. And so if we're given any polynomial in here, we're going to define its highest order term, which is why I call it h of f, to be the leading coefficient of f, which means that, well, first of all, if f is just a zero polynomial, then its leading term is defined to be 0. And otherwise, we can write f as the sum from I equals 0 to n of ai xi, where the xi's, well, those are just the powers of x, and ai are just the coefficients in a. And since this is just polynomials, n must be finite here, so this isn't like a power series or anything interesting or cool like that. And also here we take we stop at the highest non-zero coefficient. So a sub n is non-zero. So if f is non-zero, then we can write it this way, where it's in which its highest order coefficient an is non-zero, and then we just defined h of f to be an. Okay? And let P be the set of all of these highest power coefficients. Then I claim that this is an ideal in A. So let's prove it. Certainly it contains 0 because B is an ideal, so B contains 0 by definition, and we know that the highest order, I'll just call it the leading coefficient. The leading coefficient of 0 is defined to be 0, so it's in there. Now you take two things in this ideal, and we want to prove that their sum is in there. So we know that there are elements, so obviously if either A or B is 0, then the sum is just going to be one of them, and so that will clearly, it's easy to see that that's going to be in there because it's already in there. So if A and B are non-zero elements, then that means that there are polynomials f and g such that we can write f as this sum, g as this sum, and the leading term of A is A and the leading term of B is, the leading coefficient of f is A and the leading coefficient of g is B. So I guess we could make this 0 because, well, no, we better do this. We better do it this way. It doesn't really matter, so it's not worth spending any amount of time on. Well, maybe enough amount of time on to know that it's not worth spending time on. Okay, so now without loss of generality, okay, one of these two indices is going to be bigger, so we'll just say that n is less than or equal to m. Now B is an ideal in the polynomial ring, and x to the m minus n is a polynomial, so, and of course this is a polynomial because m is greater than or equal to n, so this power is greater than or equal to 0, so this product must be in B. So this thing plus this thing is in B since B is an ideal. And what is the leading coefficient of this? Well, the leading coefficient of this, the degree of this polynomial is going to be m because we've used this x here to increase the power all the way up to m. And the leading coefficient of this is going to be a. And then, of course, this has degree m as well, and the leading coefficient is going to be b. So this sum, its degree is also m, and its leading coefficient is going to be the leading coefficient of this plus the leading coefficient of this, since these two have the same degree, and it's a plus b, so therefore the sum is in there. As for closed under multiplication, you take any element r of a, then the constant polynomial is in the polynomial ring, and so the constant polynomial times f is in b, and its leading coefficient is r times a, and so r times a is in there. So therefore it's an ideal. Okay, so P is an ideal in a Noetherian ring. So by Noetherianity, which I've never seen this written down in like a textbook, but I think it's great, and I think it should be used like all the time, because it's like the most natural way to say this. Okay, even if it's not actually a word. Anyway, by Noetherianity of A, P is finitely generated, say by elements P1 through Pn. P1 through Pn are all in A. Okay? And since these are in P, by the definition of P, these are all leading coefficients. So for every single one of these, there is some polynomial in the in the ideal of the polynomial ring whose leading coefficient is precisely Pi. And now let Q be the ideal generated by F1 through Fn. And certainly since each Fi is an element of B, this ideal must be contained in the ideal B. All right? Is that actually useful at all? It might not be. Anyways, what we want to do is we're going to construct an ideal which is finitely generated and prove that the ideal that we construct is equal to this ideal B. So you might think that these F1 through Fn's are enough, but they're really not. We need more things in here, because these F1s through Fn's, like, we don't really know anything about what their degrees are. But okay, well, I'll just continue with it. Okay, so we're going to let D be the maximum degree of the Fi's, and we're going to let M be the A module in the polynomial ring which is generated by the powers of x all the way up through d minus 1. So this is a little tricky to wrap your head around. So it's generated by 1 through d minus 1, and so it's an A module, not an A adjoint X module. And that's important because basically what we need here is we need this module here to be like, we need this span to, we need the degrees of things in this span to not surpass d minus 1. So if this were an A adjoint X module, then you could use like higher order X, you could use like higher powers of X here to get outside of, to get elements here of arbitrary powers. And similarly, if this was not a module, but if we just consider this as like an ideal in AX, then you could multiply by elements in AX and get arbitrary powers. So that's why we need this, we need the thing generated by this to have degree not surpassing d minus 1. So that's why we need to consider the subset of A adjoint X, which is spanned by A and not spanned by A adjoint X. And the right sort of structure to do that is an A module structure on A adjoint X. Okay, so anyways, enough about that. So M is this. We know that M is finitely generated by construction, and we know that A is a Noetherian ring. And one of the things that we proved last time was that if you have a finite, is that if the ring, if you're talking about Noetherian modules and the underlying ring itself is Noetherian, then you don't need every single submodule to be finitely generated in order to get Noetherianity of the module. All you need is for the module itself to be finitely generated. And so in this case, since M is finitely generated and A is Noetherian, then M itself is Noetherian. Alright, so now what? Since B is an ideal in A adjoin X in the polynomial ring, it is also an A adjoin X submodule of A adjoin X, and that's sort of the correspondence you have between thinking of when you have a ring R and you have R as an R module, you have a correspondence between the ideals of R and the submodules of the R module R, and they're basically the same thing. And it's something that you need to be really comfortable with because I see it coming up over and over and over again. And it's a little tricky to wrap your head around because one minute you're thinking about rings, one minute you're thinking about modules, but they're very much connected, particularly in this way. So this needs to be really automatic to jump from rings to modules, is particularly A modules to from the ring A to the A module A. So anyways, so B is an ideal in A adjoin X, so B is an A adjoin X submodule of A adjoin X, so it has an A adjoin X module structure. But then it also has an A module structure, because for it to be an A adjoin X submodule of A adjoin X, not only does it need to be an abelian group in and of itself, but A adjoin X needs to act on it. And if all of A adjoin X acts on it, then you've got A as a submodule of A adjoin X acting on it. So in particular, this submodule acts on it. And so you have an A module structure on the submodule B of A adjoin X. So the point of this is that B and M are both A modules in... Yeah, B and M are both A modules, which are submodules of the A module A adjoin X. Okay, so you have A adjoin X with an A module structure, and then as submodules of that A module, you have M and B. Okay, and so now, I'm pretty sure I proved this when I first discussed modules, but modules are closed under intersections. And if I didn't prove it, you could just prove it. It's just an easy fact. So this intersection is also an A submodule of M. But M is Noetherian, so submodules are themselves modules. No, submodules of Noetherian modules are finitely generated, so the fact that this is a submodule of M means that it's finitely generated. Alright, and so let's say it's generated by G1 through GM. So this was important because what we're doing here is we're sort of taking we're sort of taking B, but restricting B to the things who we're sort of taking when you take this how should I say this? B has a lot of things in it because not only does it have like its own ideals, but you can multiply anything in B by any polynomial and stay in B. So what we need to do here is, in order to get it to be finitely generated, we need to sort of restrict it to a finite number of dimensions in order to get that finite generationness of the ideal. And so in order to do that, we need to intersect it with something which we know for sure is finitely generated. And the right thing to do that is to choose M. But M here, you need to there needs to be enough degrees there where you can do enough stuff within those degrees. And the right degree is to go up to d minus 1 because it turns out that that's enough, and you get that d minus 1 from these finite generators of the coefficients. Wait a minute. Yeah. These things which allow you to generate, these things which give you leading terms with which allow you to generate p. So anyways, so now we consider the ideal. So we have these, so these g1 through gm, these are all polynomials. So now let's take b prime to be the ideal generated by the f1 through fn and g1 through gm. And I claim that this is equal to b. And if that's so, then that proves that b is finitely generated because this thing is finitely generated. Okay, obviously b prime is contained in b since each fi and each gi is contained in b. So the ideal generated by them is contained in b. The other direction is trickier. So take an element in our ideal b. We'll call it f. Now, it's going to have some degree. Let's suppose its degree is strictly less than d here. If this is the case, then we know that f is in b, obviously, but also because its degree is less than d, it's in m. And so it's contained in this intersection, but this intersection is this intersection here is equal to this ideal generated by these, which is itself a submodule. No, right? This is this thing, but okay. So these are A modules. So these are like linear combinations of the GIs with coefficients in A, and that's sort of that's contained in this thing because this is linear combinations with coefficients in this ring here, and in particular the coefficients, we could take the coefficients to be in A, and we could just look at the GIs here, and then we get this thing contained in here. Okay, so therefore, if it happens to be that f has degree less than d, then f is contained in b prime. Otherwise, let's suppose that the degree of f, we'll call it df, let's say it's greater than or equal to d. Okay, so let a be the leading coefficient of f. Basically what we want to do is we want to take f, and we want to get rid of the coefficient of every single power which is above d minus 1. Okay, so let's take the highest power, a, or the leading coefficient, a. Then a is in p by definition. So a is generated by p1 through pn. And so, since it's generated by p1 through pn, there are coefficients a1 comma n, and these coefficients are in a such that this sum is equal to a. But we know that these pi's, these are the leading coefficients of the fi's. And so then what we have, oh, this is not correct. And I should not have thrown out the sheet that has the proof on this. Where is this? Ugh, okay. So, okay, yeah, there we go. Okay, so we take, we don't multiply by pi, we have to multiply by, fi, But then we also have to multiply by x to the power of d sub f minus the degree of fi. And the reason that we do that is that, okay, and this makes more sense why we had to do this here. So, I'm going to have to make one more video to finally explain this explanation. But I know if I don't stop the video here, then it's going to like break up into 2 videos. And it just won't be good. So I guess I'll finish up the proof of this in the next video.